Hey you guys, this is section 7.8, improper integrals. What the heck is an improper integral and how do we actually integrate it, right? So again, this is your FLT. Go ahead and write that down. Pause and play whenever you're ready. Given an improper integral, I will be able to evaluate it, if possible, by applying the concept of limits, okay? So you guys will get more practice with integration here, as well as understanding how limits work. So before we proceed, okay, some things that I want to cover. Suppose we take the limit as x goes to infinity. Okay, actually I'll write it a little bit larger here. Suppose we take the limit of something as x goes to infinity. Now, what if we took the limit of x squared over x to the fifth as x goes to infinity, right? What happens there? What if we take the limit of x to the fifth over x squared as x goes to infinity? And what would happen if we took the limit of 6x squared over 3x squared? So we talked about this last year. Let's refresh. When x is going to infinity or negative infinity, it's getting large in a sense. Okay, obviously negative infinity will be large in the negative sense. So x is getting very big. So when x is getting large with a fraction, it's like a race to see who gets larger faster, right? And it's based off of the degree of your function. So x to the first power, if x gets really large, it's going to grow. But so will x squared. But out of x and x squared will grow faster. Because when you're squaring a value, it just gets larger faster. Okay? X cubed will be even larger, will grow even faster than that. And so on. So basically, the higher the nth power, the faster it's going to grow, right? Now, can you guys think of the fastest growing function? Pause and play when you're ready. The fastest growing function is an exponential function, e to the x. It grows significantly faster in the long run, okay? So knowing that e to the x is the fastest growing function, what is the slowest growing function? Pause and play when you're ready. Don't worry if you didn't get this one here, but it will be the inverse of exponentials, which is log. So I'm going to draw this out for you guys so you know the rate at which things are growing. Okay? So if you take a look back here, in the first example, they're both getting larger, but it's getting larger faster in the denominator. And when the denominator gets larger faster, what happens, you guys? What's happening to the overall value? It's getting closer and closer to 0. Okay? Now, if the numerator is getting larger faster, then you know that the limit will not exist. It will just go all the way to infinity. Okay? Because the numerator is just getting way larger. Eventually, that denominator will be obsolete. Okay? Now, what if they're traveling at the same speed? Notice how the degrees are the same here, right? Then you would just divide their coefficients, 6 over 3, and that'll give you 2. You will need to know this concept very well when we jump into improper integrals. Okay? So, here we go. What the heck is an improper integral? An improper integral is when you have the integral of some function, but one of your upper or lower bounds, or both, is infinite. So, let's say we're going from a to infinity. Okay? Or let's say we're going from negative infinity to b. These right here are examples of an improper integral, when one of your bounds is an infinity. Sometimes you'll have both, but it doesn't happen very often, okay? So here's what you do. Think about this question that I'm about to pose, and then pause and play when you're ready. Do you guys remember the concept of integrating? When you integrate, what are you really finding? When you integrate, what are you really finding? Remember, you're finding the area under the curve, right? And this is where it gets a little trippy. How do you go from one number to forever? Right? It's a weird concept to wrap your head around. So the thing is, you can't theoretically go on forever because you'll never end. But we can study the behavior. So here's what we do. We're going to go ahead. Hang on one second. We're going to go ahead and instead, we're going to make it finite. Instead of a to infinity, we're going to go from a to b. But we'll find out what happens as b goes on to infinity. So you rewrite the improper integral so that it is proper, but then you just take the limit of it later. So same idea down here. Okay, we would just go from a to b, but we would take the limit as a goes on to negative infinity. Okay, so that's basically it here. That's how they wrote it formally, but let's just move on. I'll talk about all of their text at the bottom here later. Here's where it gets weird. Here's a scenario for you guys, okay? So we're finding the area under a curve. So if you are adding more area continuously, because if you're going all the way to infinity, you're continually adding more space under your curve, right? So I want you guys to think about this. If, let's say I started with 1 over 1. And let's say that value represents the area under the curve, okay? Now, what I'm going to do is I'm going to add more space to it, all right? But what I'm going to do is I'm going to increase my denominator by 1 each time. This will also represent area under the curve. So I'm adding more area under the curve, right? And let's say I keep going all the way to, I don't know, 1 over 25, right? Okay, so here's my question to you guys. If I go on forever, will the area just get larger and larger and larger and larger? Now, before I answer that question, okay? Here's another scenario for you guys. What if I started off with 1 over 1, right? And that'll still represent the area, but I want to add more area to it. But now instead, what I want to do is, I still want to increase my denominator by 1, but now I want to square that denominator each time. Why I'm doing that, you guys will know later. So the next one will be 1 over 4 squared. So I'm going to simulate this for you guys. Okay, this right here is called a summation. Okay, don't worry about writing out what the summation is. I want to show you guys right here. So here I have a summation. I'm going to go ahead and run a test, okay? Let's call this 1 to k. Now, what I'm typing out, you guys really don't need to know. 1 over... Okay, so here let's go from 0 to 10,000, and we'll slow it down. Okay, so a summation is basically just a very fast way of adding numbers, okay? So when it's 1 over 1, my answer is right there in that little tiny box that says equals 1. Now, if I change that to 2, that means I'm taking 1 over 1 plus 1 over 2. So 1 plus 1/2 is 1.5. So what I did right there was I took this and I added this. Now, what if I added one more, 1/3, right? So I could change that to a 3. So if you notice right there, in that kind of grayish box, it says 1.83333. That represents the area that I keep adding, right? So I want you guys to take a look at what happens if I just let that play button play, meaning I'm adding more and more area to it. Take a look at that value, right? Okay. Now I'm adding values at a very fast pace. So right now I'm at the 3,000th number. So I'm adding 1 over 3,000 plus everything before it. Now, what do you guys notice about the area? Is it getting larger and larger and larger? And it looks like it is. 9.3, 9.8, 9.9, 9.5, 9.6. And I stopped at 10,000, but I can go on forever, right? Now, let me go ahead and run that simulation for the other scenario. Now there I squared the denominator, so I'm going to go ahead and square it here. Now I'll slow this one down. Now at the bottom, I'm adding 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared at a very fast rate, right? Would you guys agree that if I keep adding more numbers to it, it's just going to get larger and larger? Well, let's take a look. So at the bottom here, it's at currently a 1.64. At the very top, it's growing, but if you notice at the very bottom, it's like going at a snail's pace. So here's what I want you to think about. For that second scenario, why isn't it growing? Let me rephrase. We all agree that it is growing, but notice how it's growing very slowly. So my question to you guys is, can we all agree that this will never hit 2? Okay, no matter what we do, if you guys take a look, eventually they stop touching the 1 and the 6 and the 4 and the 4, right? Maybe they might touch that second 4, but I'll let it run all the way to 10,000. Theoretically, you could go on forever. You could let it run all the way to infinity, but you notice that eventually it reaches a cap, kind of like a carrying capacity, right? In your last lesson. So it's weird because at the top, that first scenario, it just kept on getting larger and larger, but that second scenario, there was kind of like a boundary, right? And this was always a trippy concept to me because if you think about it, if you have a curve and you're finding the area under the curve if you go on forever, you would think that your area will just get larger and larger and larger, right? But if you go on to infinity, in some cases, it doesn't always get larger and larger. Actually, there's a cap to it. Okay? I know there's a lot going on there, so here's where I'm getting at. Some integrals, when you're trying to find the area of it, it will just get larger and larger. We call that a diverge. It diverges, meaning that value is no longer finite. It just goes on to infinity. Whereas some other integrals will converge, meaning that it will settle down into a value. Kind of like this second scenario with the 1.64. So no matter how far I go, eventually it's going to hit the rooftop. Okay? It's only going to cap out at about 1.64, 5 at most. Okay? Okay, let's get back into it. So it'll make a lot more sense once we get into the actual analytical piece. Here's a visual. Here, when I try to find the area as I go on forever, that has an area of 1, and we'll prove it. Whereas with this function, it has an infinite amount of space. What the heck, right? Kind of weird. So here we go. So let's prove this here. Here's example 1. Ignore that you see that it diverges, okay? So first thing I want to do, some people tend to flip out when it's written like this. So whenever it's dx over x, I like to just scoot that dx outside. So 1 over x dx. Notice how it's written improperly. So we're going to go ahead and go from 1 to b instead. I like to use b as the upper bound and a as the lower bound. But it really doesn't matter which parameter you use. But here, if I replace it with b, I want to take that limit as b goes to infinity. All right? Cool, here we go. So we'll ignore the limit part. The integral of 1 over x, you guys know, is the natural log of x from 1 to b. And from there, that's the natural log of your upper bound, b, minus the natural log of 1. And then I bring down the limit as b goes to infinity. Okay? Well, we know that the natural log of 1 goes out to 0. Okay? That's by fact. Okay? So here's where you guys have to analyze your graphs here, okay? We're finding out what happens to natural log when b goes to infinity. So think about it graphically. What does a natural log look like? It's okay if you guys forgot. But let me draw you the picture. Natural log looks a little bit like this. It's a very slow increasing function. So answer this question here. What is the limit of the natural log of b as b goes to infinity? Play whenever you're ready. So even though it's slow, it's always increasing, meaning that this limit will go all the way to infinity. So this here is infinity. Infinity is not finite, meaning that the area will diverge. Meaning that it just gets larger and larger and larger and larger and larger. It will never settle down to some finite number. Okay? And again, this will make a lot more sense when we find an integral that does converge. Okay? But just bear with me. Let's keep going. And again, ignore that it says converge there. But here we go. Okay, so we have an improper integral. There's an infinity in our bounds, so I'm going to go ahead and rewrite it as 0 to b of e to negative x dx. But I'm going to take the limit as b goes to infinity. Okay, so the limit as b goes to infinity, I'm going to go ahead and take care of this integral here. E to the negative x, requires a minor u substitution. There is a function inside of the exponential function. So we know it's the integral of e is just going to be e to the same thing, but the derivative of that highlight is going to be -1, and the reciprocal will be -1 as well. Okay? From 0 to b. Now, if you guys remember, when you have something raised to the negative exponent, you could rewrite it as a fraction. So remember that x to -2 is the same thing as 1 over x squared. We're going to use the same logic here. So -1e to the negative x, just to save space, it's going to be -1 over e to the x. Okay? So let me plug in my upper minus my lower. So -1 over e to the b minus -1 over e to the 0. And then I'll bring down my limit because I didn't take the limit just yet. And again, this is new, so it's going to look weird, all right? Okay. E to the 0, you guys should know is 1. So -1 divided by -1. Sorry, -1 divided by 1 is -1. But there's also this minus sign here, so we got something like a +1. And then I'll bring that limit down. Okay, so just think about this here. B has nothing to do with this 1. So that 1 will stay as a 1. Okay? So really, what's the limit of this right here as b goes to infinity? When b gets really large here, that denominator is going to get really large. That -1 at the top is just going to stay as a -1. So what happens when the denominator gets really large? Pause and play when you're ready. When the denominator gets really large, that thing there goes out to 0. So you're just left with 0 plus that 1, which is 1. I mean, you don't have to write it, but I'll write it here. Therefore, you know it converges. That means that when you're finding the area here, you actually get something that's really close to an area of 1 square units. It doesn't go all the way to infinity. Okay. And again, make sure that you guys pause, text me whenever you have questions. This is new to you guys, so it's okay if you have questions here, okay? All right, here we go. So here, same idea, rewrite it. The limit as b goes to infinity, 1 to b, 1 minus x, e to the negative x, dx. Okay, so first step, we ignore the limit. We'll just bring that down. Okay, so the question here is, how the heck do you guys integrate this? Is it a simple integral? It's not. Should you use u substitution? Maybe, but I don't think so. Should you use integration by parts? Probably, because there's a product, okay? There's definitely no partial fractions here. So here is where you guys would have to let u equal something and dv equal something here, okay? So here we have something algebraic, 1 minus x, and here we have something that's exponential. So remember, out of light, whatever appears first is going to be your u. So in this case, your u will be 1 minus x, okay? Now, if you guys take a look, this is a and e. You're more than welcome to use the tabular method, okay? So I'll leave that up to you. I'll just use u substitution here. So a is going to be u. Okay. E to negative x dx will be this. Okay, so if u is 1 minus x, du would be negative 1 dx. And if dv is e to negative x, the integral would be negative e to the negative x. Make sure you guys understand how I got that. That involves mental u substitution. There is a function inside of that function there, okay? Okay, so we have u times v minus v. Now, there's an extra negative there. du. I'll just write everything out. From 1 to b, from 1 to b. Okay, so I'll write it out so that there's no confusion. Now we have the limit as b goes to infinity. We have 1 minus x, negative e to negative x, evaluated from 1 to b, minus... Now, if you notice, these two negatives on the inside will turn into a positive, so we'll just get rid of that. And really, you're just left with the integral of e to the negative x dx from 1 to b. All right? The integral of that is going to be negative e to the negative x from 1 to b. Let me add in another sheet here, just so I don't have to erase anything. Okay, so I'll bring this down here. Let me rewrite everything so that there's no confusion. We have 1 minus x, negative e to negative x, all evaluated from 1 to b. And then I noticed that these two... oh gosh, hold on. Okay, because it got cut off. These two negatives in purple will come out to a positive e to the negative x from 1 to b. So notice how the whole thing is going from 1 to b. So what I'm going to do is I'm just going to clean this up a bit. I'm just going to make this whole thing from 1 to b. So it is a little bit of work, you guys, and you kind of have to be persistent and bear through it, okay? Here we go. The limit as b goes to infinity will be 1 minus b, negative e to negative b, plus e to the negative b, minus 1 minus 1, negative e to negative 1, plus e to negative 1. I just plugged in my upper minus my lower. Okay, so let's get the easy parts out of the way. 1 minus 1 here is 0. So this whole thing will go to 0. And you're just left with the e to the negative 1. So minus e to the negative 1. Okay, now this last part, I encourage you guys to rewrite. All right? Actually, I'll do it right here. E to the negative 1, I'm going to write it without a negative exponent. So pause and play here. How do you rewrite e to negative 1? That's going to be 1 over e. How do I rewrite e to negative b? That's going to be 1 over e to the b. Okay? How do I rewrite this? Now this right here is going to be e to the b at the bottom. And there's a 1 minus b, but that extra negative 1 from that negative right there. Pause and play whenever you're ready, okay? The limit as b goes to infinity. The rest is analysis, okay? B is getting really large, so think about what happens here. There's a b here. There's a b here. What happens when b gets very large? Pause and play whenever you're ready. Well, in this first highlight here, I have a linear at the top, so b to the first power. At the bottom, I have exponentials. they're both getting large, but who gets larger faster? The exponential. So when the denominator gets really large, you know that this here is going to go to 0. Same logic here. Denominator will get really large, so that's going to go to 0. So all you're left with is negative 1 over e. What does that tell you? That tells you that this area will converge. There's a finite amount of space. It does not get larger and larger. Holy moly. Cool? Text me if you guys have questions, okay? Okay, so, I mean, I'll talk about the setup, but I'm not going to do the whole thing, you guys. Sometimes you will have improper integrals with both bounds as an infinite. Here's what you would do. First, you would split it, negative infinity to c e to the x dx plus c to infinity e to the x dx. Kind of like that property back with the fundamental theorem of calculus. You could just split an integral as long as you continue. And then this is where you rewrite it. So this is going to be the limit as a goes to negative infinity of a to c e to the x dx plus the limit as b goes to infinity from c to b e to the x dx. You would do the same thing, but I'm not going to finish this one for you guys, okay? Only for the sake of time. Let's I'm debating here. Hold on, okay? Okay. Let this be the last one. This wasn't so common, but I do want to cover it because I did see it maybe once or twice. Okay, on the AP exam. Notice here, there are no infinite bounds. Okay? There is another reason why it may be improper is because of this, okay? Let me first rewrite this. This one is a little bit sneaky because it's not so visible. First, I rewrote it so that the dx is just scooted out on the outside here, okay? Most people would just integrate this, plug in their upper and lower, and then call it a day. You guys got to remember, if you remember back in AB, all differentiable functions are continuous, but not all continuous functions are differentiable. Remember, if D, then C. Same concept with integration, okay? Integration only works if the function is continuous, okay? And the issue here is you're trying to find the area from -1 to 2, but somewhere in between, that function is not continuous, okay? Namely 0. If x is 0 here, there's going to be some type of vertical asymptote. So you're traveling from -1, you're jumping over a vertical asymptote, and then you're going all the way to 2. You can't do that, right? You have to only integrate continuous functions. So what you got to do here is you actually have to stop at where it's discontinuous, okay? So here I'm going to go from -1 to b, okay? And you know what? Instead of 1 over x cubed, I'm just going to write x to -3, just to make it easier. And then I'm going to continue, and notice how I'm intentionally leaving space here, okay? Actually, I'll scoot this over because I think I need more room. I'm going to continue from wherever I left off, b. Now again, remember lower bound is usually a, but I have to keep the same parameters here, okay? All the way to 2 of x to -3 dx. What you guys have to do here is we have to get really close to where it's discontinuous. We know this function is discontinuous at 0 because when x is 0, it's going to be undefined. So we're going to get really close to 0 from the left of it. And over here, we're going to get really close to 0 from the right of it. Okay? Again, it's not super popular, but I don't want you guys to not know it. Okay? So let's keep going. Doesn't change anything really. Here we're going to get x to the negative 2 over negative 2. And if I can, I'll just clean that up as 1 over negative 2x squared, just to make it a little bit more clean from negative 1 to b. And I'm going to get the same thing here. From here, from b to 2. And then I'm going to go ahead and bring these down. Plus the limit as b goes to 0 from the right. The limit as b goes to 0 from the left. Okay. Okay, so take a look. You have to get really close to 0 from the left here. All right? But take a look here. When you plug in your upper and your lower, you should get negative 1 over 2 b squared minus negative 1 over negative 2 negative 1 squared. And the same thing here, negative 1 over 2 squared minus negative 1 over 2 b squared. It's a lot of writing, but bear with me, okay? So the whole idea of, if I give you a statement and I ask you if it's true or false, really all you need is one counterexample to prove it wrong, right? So if I can prove that one of these stupid fractions are going to go to infinity, then I know the whole thing is going to diverge. So let's look at that first, okay? If b is getting really close to 0 from the left, so from the left of 0, I'll pick, I don't know, negative 0.001. What's going to happen to that quantity right there? So you could do that graphically, numerically. I'll leave it up to you guys. You could plug and chug, but eventually you're going to get some type of negative infinity there, pretty much implying that it's going to be infinite, right? So right away you could stop there and say that it'll just diverge. Simply the fact that because this right here will go to infinity. All right? They do want to see the setup, you guys. Don't just say diverge. Like, you definitely want to show why it diverges. But that's enough to show that it diverges there. You don't even have to finish up the whole problem. Okay? I'm going to stop there. Again, don't focus on this too much. You might run into one in your example, in your practice problems, but you're really focusing on the infinite bounds, okay? So it really does assess you on what you know about the three cases, what happens when the top gets larger faster, when the bottom gets larger faster, and so forth, okay? But that's basically it. Sometimes you can evaluate integrals, and sometimes you can't, but you have to prove it, okay? Practice the problems. Let me know where I can help, and I'll support.